Welcome to the lectures on fundamentals of MIMO wireless communications. We are currently looking at the basics of information theory, or the definitions which will be very useful when analyzing the capacity of MIMO channel. Till now we have covered discrete random variables, and we have given the expression of entropy relations. We have also started the description of continuous random variables, because as we said it is important because we will be finally dealing with waveform channels. And we have started with the definition of differential entropy. So we move forward in this lecture in defining some more descriptions or some more relationships of continuous random variables, which will finally end up in helping us understanding or realizing the expression of capacity, which is used in the MIMO channel conditions. So we continue from whatever we have done, that means the differential entropy, and we move forward to describe the joint entropy, the joint differential entropy. So in this case it is similar to the discrete random variable, and for the set. So if we have the set of random variables x1, x2 up to xn with densities given by f x1, x2 up to xn, that means it is a joint density, then we could define h x1, x2, xn, which is the joint entropy, as in the same manner minus f x1, x2 up to xn times log, depending upon the base whatever you put, we have a minus, so this density goes on top up to xn, and of course dx1 dxn. And then we move on to the definition of, we write this as definition of conditional differential entropy. So the conditional differential entropy is also defined for the pair of random variables x and y with a joint density of f of x y as h of x conditioned on y, or h of x given y, as minus integral f of x y, because we are taking the expectation, times log f x given y dx dy. And this particular conditional density, you could write it as x given y as f of x y upon f of y. So using this you could expand this, and the relationship you would get finally is same as that of the earlier case, as joint entropy of x and y minus h of y. So these are some of the relationships which we will be using as we move down further. So moving on, what we now need to look at is the multivariate, the entropy. This is very important. That is the entropy of a multivariate normal distribution. So we are taking step by step forward, so that we finally end up in an expression which is very useful. So for this we let x1, x2 up to xn have a multivariate normal distribution with a mean of mu, we mean a vector mu, and a covariance matrix which is written as k, and we would use the notation n of mu k in this particular definition to indicate a normal distribution with a mean and a variance. So this, you could change the variables, but they would look similar in the way you write it. And we need to find h of x1 xn, that is the multivariate distribution, which is normal in this case. So the probability distribution, the probability density of the joint distribution x1, x2, xn is usually given by f of x I write the underscore to indicate a vector. You could find this as bold in text, is given as 1 by root 2 pi raised to the power of n. This indicates a determinant of k to the power of half, that means square root e to the power of minus half x minus mu, vectors of course transpose k inverse times x minus mu. So this is the expression of the density, and we have to find this following the first principle, and we are interested in the expression which is valuable for us. So as we move ahead, we have to write, so for continuous random variables we said it is dependent only on the density, so we have this notation h of f, which I have described in the previous lecture. So this is written as minus f of x, this is the vector, times log f of x dx, right. This is what we know. So using that we move forward and write what is h of f as minus fx. So if we look at this expression, this absolute expression that we have here, and take the log of it, what we are left with is two parts. One is this part, the other is this part. So we could write it as here we can take the natural logarithm. So either log base 2 or log base n, will take ln for ease, and then we can do for log base 2, it's the similar result. So when I take the ln of this, we get a minus sign, ln 2 pi to the power of n times determinant of k raised to the power of half. So this is what we have as the first expression, and the second expression, since it is ln, ln of e to the power of something is the expression itself. So we have a minus half x minus mu transpose times k inverse times x minus mu, right. So this is the expression you have. So for which this half can come outside here, this minus and minus adds together, so you have plus half integration of fx times this constant ln 2 pi determinant of k raised to the 2 pi to the power of n, and here again the minus and the minus cancels out, and we have a plus, and there is integral f of x. Now if we look at this term, this is a row vector, this is a matrix, this is a column vector. So what you have over here is 1 cross, let's say n, and this is a n cross n, and this is a n cross 1. So this would lead to a n cross 1, finally a product over here would be 1 cross 1. So what we have is one single value end of it here. So we still write it down, x minus mu transpose times k inverse x minus mu dx, of course. So we have this expression. This particular integral, this is a constant, this is a constant over here, so the rest of it integrates to 1. So what you have is half ln 2 pi to the power of n times determinant of k. This is one of the terms. The second term which exists is also a half, and instead of, if we look at this integral fx dx, it's basically the expectation of this term. So we could write the expectation of, and if you would see this product, you could write it as expectation over I and j, two variables, xi minus mu I times k inverse times xj minus mu j, right. This again, I repeat, this integral fx dx I am replacing by this e. This e can go inside, and you will be having expectation of this times kij inverse, that means the inverse of k times this is the element times this, and then we could bring this over here. So we will have an e of xj minus mu j times xi minus mu I times k inverse of ij, right. So when we have this and the summation over ij, what this term would finally lead to is an expression which is like half this expression. What you would see is kind of kij. K is the covariance matrix, so you'll be left with the expression which is summing over k inverse all of these values So basically K inverse would be an identity matrix, and then you are basically adding up all of the terms, so you are left with half of n, and here what you have is half ln 2 pi raised to the power of n times determinant of k. So this half n that we have over here, so for ease what we could do is we could have things in a nice way, and here we could instead put this as ln of e. So if we have ln of e, then this is equivalent to 1, and then again we could modify this term to say that it is half e to the power of n, ln, half ln e to the power of n. So we have this term and this term added together, which would lead to half ln of this plus ln of this. So that means ln comes inside as a product, 2 pi e to the power of n times determinant of k. So this is the entropy. If it's ln, it's in nats. Otherwise, if it's in log base 2, it is half log base 2 2 pi e to the power of n times determinant of k is in bits, right. So this is the expression that you have for h of f, and this is what we wanted to find, and this will turn out to be very, very useful. This particular expression is going to be turn out to be very, very useful for all our expressions that we finally lead up to. So at this point I would like to point out one more thing, that is, this what we have done is for real valued. What we also need to do for complex valued, because we will be finally dealing with complex valued. So I'll just give you the result what it appears for complex valued, because that is what we need for the MIMO channel capacity. So when we have the multivariate Gaussian distribution or complex multivariate Gaussian distribution, in this case you could write the distribution as p of, or let's write in the same notation, p of x, f of x is equal to 1 upon pi to the power of n determinant of the covariance matrix e to the power of minus x minus mu times k inverse, this of course a Hermitian on top, times x minus mu. So this is the expression. So if we use this expression in calculating h of f would turn out to be log of pi e to the power of n times determinant of k. So this is the other expression which would be of value to us. So we have seen two important expressions which are fundamental in the expression of capacity, which we'll finally look at. So let's move on further from this point. So this is one of the expression that we have, and the other expression which we had pointed out is here. So these are the two expressions that we have which we'll be using in all our calculations after this. Further, as we move on, we would also like to see the relative entropy. As we have seen relative entropy for the discrete random variable case. So here also it is the Kullback-Leibler distance. It is defined as d of f to g, where f and g are two distributions, as integral f log f upon g, which is similar to the expression that we had before. So we'll use this and we'll define mutual information for this differential, for this continuous random variable, as defined as integral f x y log f x y upon f x times f y dx dy. So again, using this, the end result that we get is I of x y, similar to that we have got in the discrete random variable case, h of x minus h of x conditioned on y, or we could also write it as h of y minus of h of y conditioned upon x. So the expression looks similar. There is not much difference in the expression, in textbooks you could find all of these. So these derivations or these expressions that we have done now, these are easily available in books on information theory. One of the easy books to read, very easy to read, is the one on elements of information theory by Thomas and Cover. There are many other books. As I have always said, that you can choose a book according to your own preference, and this is the particular one which gives these expressions in a straightforward manner, which could be of direct use to you in this particular course. Again, I am iterating that we are not getting into the details of information theoretic results. We are just reviewing them because they are so fundamental, without which we will not be able to build upon the expression of capacity. So we are doing this because these are the elements which is going to support the expression of capacity finally. So we are mainly interested in using the results from information theory, for which we are undertaking this activity. Okay, so moving on further, what we have is that D, that means the relative differential relative entropy, D of F to G is greater than or equal to 0. We have seen this thing in the case of discrete random variables, and this is with equality, of course, with equality if and only if F is equal to G, almost everywhere in that set. So let S be the support set. We have defined the support set of F. We have defined support set, that is, this is the set where the probability density is greater than 0. So that is the support set of F, and then we have minus D. Again we do it in the same way, minus D of Fg. We begin with a minus. You could do it other way also, within the support set F log of G of F. Now you would remember from Jensen's inequality, this is a concave function, so we could write this as less than log of F G of F. So what we have done is this is the function, and integral over F df is basically the expectation operation. So expectation of a function is greater than or equal to the function of the expectation of the variable for convex. For concave it is the reverse. So that is what we have over here. So this is equal to log of this, and this cancels, G, and this is basically log of this, basically integrated over S, the support set. So basically the probability density function when integrated over the support set leads to 1. So basically log of 1, which is equal to 0. So that critically means that minus D is less than or equal to 0, or in other words what we have is D of F from G is greater than or equal to 0. So this also holds true for the continuous random variable case, as we have seen for the discrete random variable. Now this gives us some important result, because we have defined mutual information in terms of relative entropy. You could also start with this definition and you could prove many things as well. So D is greater than or equal to 0, therefore we have this I x y is also greater than or equal to 0. So basically if I x y being the definition of D, it is greater than or equal to 0, so which in other words mean that H of x is greater than or equal to H of x conditioned on y, or again H of y is greater than or equal to H of y conditioned on x. So that means conditioning reduces entropy. That is what we had seen earlier. Same thing holds in this particular case also. We don't have any different result. Now with this we'd like to move on to a very important result at this stage, where what we have seen is expression of entropy, and we have seen also expression of the entropy for Gaussian distribution. We have also seen expression of entropy for multivariate Gaussian distribution for real as well as for complex case. So what we'd like to see is which distribution maximizes entropy. Now this could be done in many ways. One of the ways doing it straightforward way, like finding the distribution which maximizes. The other one that we could do is to propose a distribution and see that okay, this distribution whether it's the maximum or not. So that is the second approach, is the one that what we are going to follow in this particular case. So we say that let the random vector x, which is an element of Rn, that means an n dimensional vector, have 0 mean have 0 mean and covariance given by k is equal to E of x times x transpose. Right. So, this is how you define the covariance matrix, and that is k I j is equal to E of x I x j. Right. E is the expectation operator for I lying I and j both lying between 1 and n. Then if we say this, then we can say that h of x is the differential entropy of x is less than or equal to half log of 2 pi e raised to the power of n times determinant of k with equality if and only if x is distributed as a normal distribution with 0 mean and covariance matrix given by k. So, if we look at this, what we are saying is we are proposing that the maximum entropy of this random vector x is determined by this expression. Now, if you remember this expression, it is the entropy of multivariate Gaussian distribution, and where k is the covariance matrix. So, what this is saying is that suppose you have a random vector x whose covariance matrix is given by k. All this is saying is that the entropy of such a random vector whose covariance matrix is given attains the maximum value when the distribution is normal and the entropy is given by that of the normal. So, any other random vector would have an entropy which is less than that of the normal vector whose covariance is the same as that of the vector which is given. So, to do this, again we will take advantage of d. So, we will begin with that d is greater than or equal to 0. So, this is well known. So, this is where we begin with g and phi k. So, where we assume that this phi k in our expression is normal distribution, and we assume that g of x is any density satisfying integral g of x xi xj dx is equal to k I j. This is the element of the covariance matrix. So, all this is saying is that this is the definition of the element of the covariance matrix for all I j, and phi k is normally distributed with 0 mean and k as the covariance matrix. So, we equated the covariance matrix and we have said the mu is equal to 0. So, when we take so basically we will be using the distance of g from phi k and we will be showing the important result. So, when we move forward, we look at this expression. This is basically g log g upon phi k, right. So, if you look at the numerator, it is a minus g log 1 upon g. So, or g log g. So, basically it is minus h of g, right. So, this is the from the numerator, and from the denominator term you have integral g log phi of k. So, when we look at g log phi of k we said it is 1 by 2 pi to the power of n times determinant of k square root of that e to the power of minus half x minus mu. So, in this case mu is 0 transpose k inverse x minus mu, right. This is what we had. So, if you take log of phi k, we have seen this expression, there is a constant term which goes there. So, basically log of 2 pi to the power of n times determinant of k half, this is one of the constant. And if you take a look at the second term, you again have, okay, there is a minus half, depending upon the base you are going to have a 1 or a log of 2, a log of e, and then you have x times k inverse x transpose times x. So, basically there is a constant, there is another constant, and there is a quadratic term. Okay. So, what we have said is basically this term, if you look at this term, the g times the quadratic term is what you are going to encounter over here, and g times the quadratic term is equal to k. And we could also say that this could be replaced by integral of phi times log of phi k, because what we have described in this is that the covariance of this random vector x and that of the normal distribution are basically same. So, we have taken a normal distribution which has this. So, if I would do integral phi log k, what we are going to encounter is this term. So, in this term when we do the integral, so this would turn out to be 1 whether we have a phi or a g. So, whether we have integral phi or we have integral g along with this term, the integral terms to be 1 times the constant. This is the same constant which is due to log phi. So, we have integral g times the quadratic term in one case here, and in the other case you are going to have integral phi times the quadratic term. So, these are the two things that we have. So, as we have said that g times the quadratic term leads to k, leads to the expression of k, and again phi times the quadratic term is also equal to k, because these both lead to the expression of the covariance matrix. So, since they are equal and this integral turns out to be the constant, because integral of phi times a constant is equal to 1, integral of g times the constant is equal to 1. So, all we are left with these terms again which are equal by virtue of this covariance. So, then we could replace integral phi log g log phi with a phi log phi. So, what we have over here is minus h g of phi, and we have minus over here. So, that would lead to minus h of g plus h of phi if you look at this expression. So, all we have done is replaced integral g log phi with integral phi log phi, because log phi leads to expression where there is a constant and constant times a quadratic term. So, integral of constant times g is equal to the constant, and integral of the constant time the quadratic term is equal to the same constant time the quadratic term as for the normal case, and they are both equal to the k component. So, I could replace g with phi. So, this is equal to minus h of g, and this whole expression is basically h of phi. So, since this is greater than or equal to 0, all we can say is that h of phi is greater than or equal to h of g, and h of phi is the expression which we already have, is given by this. So, basically h of phi is given by this expression. So, overall we could say that this holds true for any continuous random vector whose covariance is given by k. So, we conclude this particular lecture at this point. The very important things to remember is we have come to the point where we have shown that Gaussian distribution or multivariate Gaussian distribution gives the maximum entropy for any random vector which has the same covariance. Thank you.